Okay, Reynolds transport theorem. What is Reynolds transport theorem? Well, Reynolds transport theorem can be thought of as a function or a device or a mechanism. A device or a mechanism which takes closed system, conservation laws, takes closed system conservation laws and produces the equivalent open system. Conservation law, or equation if you like. Reynolds transport theorem, okay? You pump in a closed system energy balance, let's say. You provide it with the closed system energy balance in the form that we see it here, and it spits out the open system energy balance through some procedure, okay? So we're going to be deriving this Reynolds transport theorem, this equation or relationship that allows us to go from closed to open system conservation equations. Now, let's get started. Let's say we have a region in space. So here's our region in space, okay? It's like a pipe or a channel of some kind. Now, the boundaries of my pipe or channel and the region in space are defined by my control volume, which is the dashed line here. So the dashed line is my open system control volume, okay? The dashed line is my open system control volume, or if you like, CV, control volume, CV, all right? Now, at a particular time, time equals T1. At a particular time, time equals T1. There is a certain amount of mass in my system, a certain amount of mass in this control volume here, and all that mass I'm going to label or dye with this cross-hatched chalk here. So initially, my system coincides with my control volume, my closed system. So I'm going to label all the mass inside of the control volume at time T1. All that mass inside the control volume, I'm going to define that as my closed system. And I'm going to be examining this closed cross-hatched system as it flows through this channel. Okay? So mass is flowing through this channel, and at a given time, I'm taking a snapshot, and I'm putting dye and marking all the mass encapsulated with my control, by my control volume. Okay? So that's how I'm defining my closed system. So the amount of mass, or let's say beta, could be mass, could be energy. The system has a certain amount of beta in it. The beta could be mass, it could be energy, but at some time t, I have a certain amount of beta in my control volume. So beta in my control volume at time t is equal to the amount of beta in my closed system. At time t, because I've defined them to be the same at time t. The amount of beta could be energy, could be mass in my control volume here. My open system, mass is flowing in and out. The amount of beta in the control volume at time t is by definition the amount of beta in my closed system. because my closed system, I've tagged all the mass at time t within my open system, my control volume, and I've called that my closed system fixed quantity of mass, okay? So beta within the control volume at time t is equal to beta within the closed system, beta of the closed system at time t. Now let's go to a time t equal t1 plus delta t. So I'm going to let time roll on, and I'm going to take a snapshot of what my channel looks like. So here's my channel, and here's my control volume. Here's my control volume, all right? Now mass is flowing in, and mass is flowing out, okay? Now there's a certain mass flow here, m dot in, and a certain mass flow out, m dot out, okay? And I have a certain amount of beta per unit mass at the inlet. So I have beta at the inlet, and I have beta at the outlet. Okay? So mass is flowing in, mass is flowing out of my control volume, and by the way, beta per unit mass, that could be energy, it could be something else. Beta per unit mass, I know that at the inlet, and I know that at the outlet. Now, because the mass is flowing in and out, my system is getting pushed through the control volume. So at some time t1 plus delta t, the system, my cross-hatched closed mass system, has now been forced through in and out partially of my control volume. So that's what the system, closed mass system, looks like at time t1 plus delta t. T1 plus delta t. Now, how much beta? That could be energy, it could be mass, who knows? How much beta do I have within my dash line, my control volume at time t1 plus delta t? I guess I'm calling it t1 here. Put a 1 there, all right? So the amount of beta that I have in the open system, beta in the control volume or open system at time t1 plus delta t, well, that's going to be equal to the amount of beta in my closed system. So beta in the closed system at t1 plus delta t. I should make this approximately equal to. These are estimates. The amount of beta within the control volume is approximately equal to the amount of beta in my closed system, plus the amount of beta that is flown in across my control volume boundary. So plus B in m dot in times delta t. M dot times delta t gives you mass. So the amount of beta that's flown into my control volume is beta per unit mass times the amount of mass that is flown in. Okay, so that's why we have this m dot plus delta t. And then the amount, and then I got to subtract off the amount of beta that is flowed out of my control volume. So I have minus B out, m dot out, delta t. So this is inflow of beta outflow of beta. So let's read this in words here. The amount of beta within my dash control volume, my open system, is approximately equal to the amount of beta that's in my closed system, that's the crosshatch, plus the amount of beta that's flown in due to the mass flow, minus the amount of beta that's flowed out due to the mass flow, okay? Okay, let's subtract this equation from this equation. Let's subtract one equation from the other. I really don't want to erase this, but I think we're going to have to. Make sure you have this copied down in your notes. If not, pause the lecture and copy it down. So let's subtract beta in the control volume at time t1 plus delta t from and beta within the control volume at time t1. So I have beta within the control volume at time t1 plus delta t minus beta within the control volume at time t1 equals, or approximately equals, beta within the closed system at time t1 plus delta t minus beta within the closed system at t1 plus the inflow of beta minus the outflow of beta. So I have B in m dot in delta t, so this is the inflow, minus the outflow times delta t, okay? Now, let me divide this equation, both sides by delta t. The difference in beta at time t1 delta t and t1 divided by delta t, that's for the control volume. Similar term here for the closed system, and then I got the outflow and the inflow per unit time. Now, let's take the limit. Limit delta t goes to 0. Let's let delta t become a differential. What does this term become right here? This becomes d beta within the control volume dt. D beta within the control volume dt. The approximation becomes an exact equality. Then I get d beta in the closed system dt plus b in m dot in minus b out m dot out. So we have a differential equation now. We've taken the limit, delta t goes to 0, and my approximation becomes an exact. So what does this say? What does this say? This says that the rate of change of beta within my open system control volume is equal to the rate of change of beta within my closed system that's flowing through the control volume plus the inflow of beta minus the outflow of beta per unit time. That's what that equation means. So this is rate of change of beta within the control volume, rate of change of beta within the closed system, which is flowing through my control volume. And then I have, if you like, the net inflow per unit time. Net inflow per unit time. That's what that equation is in words. Now, I'm going to clean up this equation a little bit. First of all, first thing I'm going to do, in this derivation here, this channel, I had one inlet and one outlet. What if I have multiple inlets and outlets? Maybe this is some weird machine and I got a bunch of stuff coming in and a bunch of stuff coming out. So I'm going to rewrite this equation here. I'm going to rewrite this equation, assuming that there's maybe multiple inlets and multiple outlets. So I'm going to put summation signs here. And I'm also going to flip the equation. I'm going to take this d beta dt for the closed system. I'm going to put it on the left-hand side, and I'm going to put d beta for the control volume and put it on the right-hand side. Okay? So I'm going to kind of flip the equation. I'm going to kind of flip the equation here. So let me rewrite the final version, which takes into account multiple inlets and outlets. And I'm going to put the d beta for the closed system on the left-hand side. D beta dt, the rate of change in beta within the closed system, is equal to the rate of change of beta within my control volume plus, now the signs are going to flip on the B out and the B in term, the flow of beta in and the flow out, because I'm going to put this over on the other side of the equation, and I'm going to flip the whole equation. So I'm going to have multiple inlets and outlets, the sum of beta m dot out minus the sum of m dot beta m dot in. I think I'm going to put m dot beta first. I don't know quite why I'm doing this. M dot beta per unit mass, m dot beta per unit mass. Outlet minus inlet. Box this equation up. Box this equation up. This is what's called the Reynolds transport theorem. Reynolds transport theorem. Reynolds transport theorem, or if you like, RTT. This equation here allows you to move or transform a closed system conservation equation into an open system conservation equation. So let's go over what these terms are again. Rate of change in closed system beta, rate of change in beta in control volume, rate of change in beta control volume, rate of change in closed system beta, and then we have outflow of beta, inflow of beta. Again, why do we have these summation signs? Because we may have situations where we have more than one inlet and one outlet. So we're going to have to sum over all inlets and sum over all outlets to get the proper flow of beta in and out of the control volume. Reynolds transport theorem. Let's apply this to conservation of mass. Let's apply this to conservation of mass. Recall, we had a little table up here. I'll put part of the table in. I'll try to squeeze the table in. Good enough. So we have extensive prop. I had energy, I had mass, I had beta here. Beta was energy, beta was mass, and then I had beta per unit mass. So I had E per M, or lowercase e, and I had M per M, which was 1. And the conservation equations were d beta dt for the closed system is equal to q dot minus w dot, okay? And then mass, I had d beta mass dt for the closed system. What's the change of mass in a closed system? 0, okay? Change in mass in the closed system, 0. So this is the table that we had just a little bit ago. Let's apply the Reynolds transport theorem. Let's apply the Reynolds transport theorem. This guy to mass. Apply Reynolds transport theorem to beta equals mass. Okay? Seems like I'm running low on chalk here. Well, so let me write the equation down. Reynolds transport theorem. D beta dt, and that's for the closed system, is equal to d beta dt for the control volume plus the sum of m dot beta out minus the sum of m dot, beta per unit mass in. And the picture here, let's say we have a system and I have multiple inlets. Multiple inlets. So here's a system with a bunch of mass flowing in. And a bunch of masses flowing out. So we have m dot in 1, m dot in 2, dot, 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 all the way down to m dot in n. And then I got a bunch of masses flowing out, m dot out 1, m dot out 2, dot, 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 all the way down to m dot out n. My system is the open system, which you can see here. And I got mass flowing across the system boundary in all sorts of places. So this is the control volume or open system. Why is this an open system? There's mass crossing the system boundary in all sorts of places. Open system. Okay? So there's Reynolds transport theorem. Let's apply it to mass. This guy. Well, beta per unit mass, B is 1. So these B's here in the flow part of Reynolds transport theorem, these B's become 1. Okay? Beta per unit masses, those all become 1. d beta dt for the closed system is equal to 0. No change in mass with respect to time for the closed system. So this term, d beta dt for the closed system is 0. And beta in the control volume is mass in the control volume. Mass within the control volume. Okay? So let's write what I have. 0 is equal to the time rate of change of mass within the control volume plus the sum of the mass flows out minus the sum of the mass flows in. Let me put the flows on the left-hand side of the equation and then flip the whole equation. The time rate of change of mass within my control volume. So I have a certain amount of mass within the control volume. The rate of change of mass within that control volume is equal to the sum of the inflows minus the sum of the outflows. Rate of change in m in mass in control volume is equal to the net inflow. Inflow minus outflow. Net inflow of mass. Put a box around this. This is the mass balance. This is the mass balance for an open system. Very simple equation, and it can be applied to an open system. All right? Okay, we're going to leave it at that. We'll do an example involving an open system mass balance next time. I think we've done enough today. This is quite a jump. So let's just review a little bit here. We developed the Reynolds transport theorem, which allows us to transform closed system conservation equations. They have a d beta dt for the closed system in the expression to open system conservation equations. It's the Reynolds transport theorem. And we applied it to the simplest possible application, which is conservation of mass. Conservation of mass says that the change in mass within the system, time rate of change of mass within the closed system is equal to 0. d beta dt for the closed system, when beta is equal to m, is equal to 0. And then we applied the Reynolds transport theorem for beta equals mass. And we have that the change in mass within my open system is equal to the net inflow. In other words, the inflow minus the outflow. Okay? We'll do an example to solidify the application of that equation next time. Okay? But I think we're in good position. We'll also, once we're done with that next time, we'll apply the Reynolds transport theorem to energy and develop the energy conservation equation for an open system. I think that's enough for today.